Okay, so you've had an action potential. Now what? Well, let's go back and look at the electrotonic currents that we talked about earlier. And just for the sake of simplicity, we're going to keep it to talking about positive currents, although we will address negative currents at a later point in time. It's just, for right now, we just want to keep it simple. I want you to kind of get inside of an action potential, understand it from the inside out, rather than just be able to memorize it and kind of repeat it back to me as though it were some empty, colorless fact. I want you to really sense what's going on in this dynamic process. So here we have a presynaptic terminal that's synapsing on a postsynaptic dendrite. We know that there's been an action potential in this presynaptic terminal because we see that there is release of something at the synaptic cleft. So here we have the release of something that's binding to something here, probably receptors, and moving a current inward, a positive current inward. And we know that there are already positive ions in the cytosol, positive and negative here. And we also remember what happens, that charge repels like charge. So when you move a positive charge into the cytosol here, the positive charges that are already there will be moved away from the positive charges coming in, and that's what creates the currents. Now these currents move relatively quickly, but we also know that we have a leaky membrane, and so we start to lose that current along the way. So by the time it gets down here, if it's just this current, there's not enough depolarization here to trigger the action potential. But we also know we have another input over here that's delivering a positive current here, leaking out, but the two together are additive. And when we get to the initiation site here, the membrane is depolarized sufficiently to generate an action potential. And even though we know we're going to lose a little bit of the current here, this membrane is loaded with sodium and potassium gates, so we know that the area just adjacent to this action potential will also depolarize sufficiently to generate another action potential, and so on down the length of the axon. The problem with this is, although the electrotonic current is pretty darn fast, this opening and closing of channels of gates here slows that current down a bit, so that it could take a great deal of time for an axon whose cell body is located in the spinal cord, let's say a motor neuron. It could take some time for enough action potentials to be generated to get that signal down to, let's say, your ankle. So here we are again. We have an action potential at the initiation site. Bam! Sodium gates open up. Sodium comes flooding into the cell, depolarizing the membrane. Sodium gates close. Potassium, voltage-sensitive potassium gates are open. Potassium leaves the cell. So we're starting to repolarize, or moving towards hyperpolarization. But we also have current moving through, positive current moving through, enough such that another action potential is generated. More sodium gates are open, and the signal is propagated down the length of the axon. Now, the reason that the action potential moves in one direction is that at this point, remember, the sodium gates are closed and they can't be reactivated for a while. We have hyperpolarization because potassium has moved out of the cell, and consequently we can't generate another action potential going backwards. So what we have here is this bam, 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 opening and shutting of sodium and potassium gates. And while it's a much more efficient way of moving a signal down an axon than is an electrotonic current that kind of leaks out of the axon, it's a bit slower. But for signals that need to be transmitted quickly, you need to jump really fast away from a burning tree or something. Nature has found a way to overcome this drawback. What we have, certainly not in all axons, but in many axons, especially when quick signal conductance is needed, we have what's called myelination. And what this myelination does is it gives us these rather long stretches in between these gates or places of action potential where we can move from an action potential and a gated response back to an electrotonic current. So we have bam, bam, whoosh, bam, bam, and it's a much faster signal. And the reason we have the whoosh is because the myelination keeps this current from leaking out that it would do otherwise on this membrane. So it's kind of like this. Bam, 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 and then whoosh. So the sodium gate is opening, sodium gate is closing, potassium gate is opening, repolarizing the membrane, but that current goes through that myelinated area, whoosh, very quickly down to the next set of gates. And then again, sodium channel opens, sodium channel closes, potassium channel opens, hyperpolarizes, but the current goes down that nice smooth path. And you will hear this type of conduction referred to as saltatory conduction, from the Latin word for jumping or dancing, and that's essentially how it's described. It's described typically as a current that jumps from this point to this point to this point to this point. But as you've seen, that's not really what happens. What happens is that these gates open up, these gates open up, you have a current that moves through very quickly here, starting another action potential very quickly here, another action potential very quickly here. So it doesn't really jump from node to node to node, as you see in so many books. What also contributes to the rapid propagation of the signal down a myelinated axon is the presence of high concentrations of voltage-gated sodium channels at the nodes of Ranvier, so that when this current speeds down through this myelin and reaches the node of Ranvier, you have a bunch of voltage-gated sodium channels that then open up and perpetuate the current or propagate the current further down to the next node. And so the next time we're going to talk about what happens when that action potential, whether it's in a myelinated axon or unmyelinated axon, gets all the way down to the nerve terminal, what happens at the synaptic cleft. Now, everything you've seen in this video to this point has been really a grossly oversimplified version of what is actually going on and what's actually present. That said, I hope this gives you enough of a sense of the feeling of it that you can now go back to the textbook and kind of, weed your way through that with a better appreciation at a very simple level of what's going on. So until the next time, this is the end.